3.3 is on coordinatization of vectors. And basically what this is going to do, I'll give you the gist of it before we get going, is because the vector spaces have a defined operation and you have some of the properties that you have unique combinations of your scalars are, you essentially can map your one vector space into the other vectors to another vector space, and like a one-to-one correspondence. So we say it's one-to-one and onto. So this is called an isomorphism. And one will be just some vector space, but we can relate it to any vector space in Rn. And essentially has the same structure of what's going on. So let's get to that concept. We'll come back to that. So first, about set notation. So I wanted to just go over this briefly just to remind you about set notation. So when you have sets, say 1, 2, 3, in just a set, whether you write it as 1, 2, 3, 2, 3, 1, or 3, 2, 1, we say those sets are equal. So these are the same or equal sets. So when you talk about a regular set, it is not ordered. When you prove one set's equal to the other, you pick an element in here, and then you show it must be, or whatever. You pick an element in here, and you show it must be in here. And then vice versa. You pick an element in here, and then you show it must be in here. So you say let X be in here, and then show it has to be in the other, and vice versa. So it's subsets of each other. And so the order doesn't matter when you just talk about basic set notation. So they're not ordered. So now we're going to define an ordered basis or an ordered set. And that's going to have to do with, like IJK, like it matters that it's IJK. So, and then how we set it up. So this is a little bit notation and vocab. This is an ordered basis for Rn. So we can use capital E. So E, and we just use parentheses. And then we say that's E1, E2, etc. to En. So for R3, an ordered basis would be just E1, E2, and E3, which literally would be IJK. So it would be I, J, and K. So, and those are called the standard basis for R3, which we know that. So now we're going to let V be a finite, so we're going to stay in a finite case, finite dimensional vector space. So let V be a finite dimensional vector space. I'll abbreviate that. And let B equal B1, B2, etc. to B sub n, be an ordered basis for V. So it's some vector space, right? It doesn't have to be Rn, but this is what you can do. So it's an ordered basis for V. By theorem 3.3, I should have put that down there. That bugs me. Okay, so by theorem 3.3, every vector V in V can be expressed in the form. So this is when you're saying it's a linear combination where all those coefficients are R's. So you take some vectors V, but that vector can be expressed in this form. So everything in V can be expressed as a linear combination of the basis, right? So you'd say V is equal to R1 B1 plus R2 B2, etc., plus all the way to Rn Bn. And that is for unique, whoa, pen's getting weird here. Okay, we're going to switch pencils. I'm not sure what that's doing. That could be low on juice. Okay, so for unique R's, where am I? So for unique R sub i's in R, we associate the vector R1 to Rn in Rn. So we're essentially what we're going to do is we're going to just take those coefficients, right? We're going to take all these coefficients, R1 to Rn, and just, we're going to basically make a correspondence between whatever vector and that R that will be in Rn. Okay, so that with V and is called the coordinate vector V related to the ordered basis B. Let me write that out. So, and is called the coordinate vector V related to the ordered basis capital B and denoted V sub B equal to, and then you're putting in just the R's, R1 to Rn. And so that can be true if it's, you have your polynomials or your matrices or whatever. You will have every vector can be expressed in this form. And so we're going to make that correspondence to those R's, and we're essentially we're going to be able to do everything you can in the vector space in Rn, well, I mean, those vector space operations, and just use whatever is in Rn, more or less. So it's a way to make a connection. And allows us to talk about some other stuff about sets and stuff. So let's look at this example. And this will really be it. We're not going much further than this. So this is example number 5. I mean, it's number 5 on page 211, which says, I won't write the whole thing up, but it says, find the coordinate vector of the given vector related to the indicated ordered basis. Okay, so our given vector is this. And guess what? We're going to row reduce. So you're basically finding those r's is what this is all about. So then you're in R3. This is our vector v. And so we're not doing anything fancy here. We're just going to say this is v in R3. So find those other vectors. So your ordered basis b is given. So it's parentheses, and this is your ordered basis. So b1 is 1, 3, negative 2. b2 is 4, 1, 3. And b3 is negative 1, 2, 0. So b1, b2, b3. And so you basically, what you're doing is you want to say what r's times this, or I'm sorry, what r's times these give you that. So you're solving a system again. And so what you're doing, so you're basically doing your you're doing your ax equal to b concept where your x values are your R1, R2, sorry, going too fast. Your x values are R1, R2, R3. And so those are your coefficients of these to equal that. And so your matrix then will be, we'll try to set it up first ahead of time. So this is 1, 3, negative 2, 4, 1, 3, negative 1, 2, 0. And this is 3, 13, negative 1. Okay, so that, I mean, that's solving the system, right? I mean, I didn't do all the little details here like I've done in the past. So you're basically saying r's all in here equal to that. So here's R1, R2, R3 equal to this, and then you're finding that coordinatization. So that, to just row reduce it, and you'll get the identity matrix. And you get 2, 1, 3. So that's your vector. That's your coordinate vector related to the ordered basis. And so we say 3, 13, negative 1, that's your ordered basis vector related to 2, 1, 3. And so and then you could do that for that kind of concept for more than just B. Might be slightly more difficult, but essentially you're solving to find what values of R would allow you to construct that vector V. Now, these B's have to be the same. I mean, they come from V. So it has to be the same type of thing. Like this could be a polynomial, and these are polynomials, but the goal is to find those coordinates, coordinatization. So it is to find the R's. So what that does, kind of the more important idea here, by renaming the vectors in V by coordinates relative to B, the resulting vector space Rn has the same structure as V. And what we say, and okay, I'm going to copy that over. Oops. Linear transformations is next. You can see it there. Okay, so I wanted to. So this is what I just said. I'm not going to write that all out. And I'll talk about isomorphism. Okay, so write this out just for sake of discussion. Okay, so don't want that right there. Okay, so rename. So you're essentially renaming the vectors corresponding to those r's, right? Those coefficients. Relative to B, resulting vector space in Rn is what you end up getting. It has the same structure as that given vector space. So what you have then are two sets. So what you're doing by doing this concept, if you have two sets V and W, and they're vector spaces. Okay, so these are both vector spaces. Then what you have are two sets, and you're setting up this correspondence from one set to the other. And when you set up this correspondence, so this is V and this is W, and you have a one-to-one correspondence, and it maps everything that's onto. So we call that one-to-one and onto. So it's the whole target is used up, so you don't have leftover things. So when you have a one-to-one and onto correspondence, that's called an isomorphism. Or it's isomorphic. So an isomorphism or of isomorphic essentially has the same structure as the other set. They're essentially the same operation, same thing. When you can set up an isomorphism. Okay, next is linear transformations, and that is it for 3.3. That's all we have.